Are you guys okay if I teach without the mask? Okay, okay. Maybe when I come close, then I will put on my mask. Okay, so it's about 3 o'clock. Yeah, very good afternoon to everyone. Welcome back from the holiday. So welcome to the class of Introduction to Linear Algebra. So this is the GE course. So maybe it is not as formal as a mathematics course. So mostly we'll learn the computation and how to understand the concept. And good to see some of my students back. Yeah. And also some badminton friends in my class. Okay. Um, yeah. So my name is Seng. And then nice to meet you all. You can call me Seng. You don't have to address me professor or doctor or anything. You can just call me Seng. And my office is A4448. Okay. If there's anything, you can email to my email address. Just my first name dot last name at xmu.edu.mo. Okay. So first thing you should check is the Moodle. Okay. Make sure that I have already enrolled you into the Moodle. And if you are not, you should email me and I will do it soon later. So the textbook we are using is Linear Algebra and its Applications by David Lay. And I already put out the PDF version of this textbook. So I turn off the okay. Is it better to see? Okay. Yeah. So if you are looking for more exercises, I suggest you to look for these books. And if you want to more reference, you can read these books as well. But mostly we were based on this textbook here. And I already put on the PDF where you can find it down here. Okay. Anything course related information you can find in this course information. I will update it from time to time. Okay. So this has all the details, our club schedule, and the structure of this course is I plan to have 40 minutes of lecture, okay, every hour, and then about 10 minutes of tutorial. So about 5 minutes for you to discuss, and then 5 minutes I will explain how to do the question. And then 10 minutes break. Okay. So each hour we'll have a break. Uh, if you came to my class before, so I encourage you to ask questions at the start of every lecture. Okay. We will spend about 10 minutes or so to discuss. You can bring in your question every lecture, every day. And I never experienced this short semester before because in this short semester, you need to learn 9 hours of new material every week. So it's quite intensive, also intensive for me. Okay. So we both have to work hard. Okay. So every day you can bring in some question to us. Okay. Before lecture, we will address it. And then I plan to have my office hour from 1 to 5 on Wednesday. Can you check your timetable? Does that suit you? So during the office hour, you can come to my office. Okay. A4448. If it doesn't suit you, you should email me and then we see what we can look up. Textbook already mentioned, suggested. So content, we have 7 topics. We're not covering all the subtopics, but I will put out suggested readings or pre-reads before the lectures. Okay, if you notice. Later, I will show you again. And assessments will be 40% of quizzes, and then final exam 60%. Okay, so final exam content consists of most of the percentage. So we have 4 quizzes every week. We got a quiz starting next week. Okay, week 2, week 3, week 4, week 5. Okay, so that you are prepared for your final because we don't have assignments in this class. Okay, so quiz 2, 3, 4, 5. So we plan to do it on Wednesday, but we will update you again. Okay, so this is the lesson plan. Okay, about 1 week we have to finish 2 topics. Yeah, so be prepared. Okay, so there's a forum. So announcement, I need to explain a bit. Last time I didn't use this early. So announcement, I will make announcement here. Okay, student forum is for you, so you can post any question on that, and then among yourself, you can reply to your friends or reply to the others' questions. Okay, any course related material you can post it here. Okay, but be respectful. Don't post anything that's not inappropriate. And if you are shy to say it out in the class, you also can post your Q&A question here. Okay, so you post it to me. Okay, for this forum, you post it to me. The question I will answer, or I bring to the class and answer. Okay, so the third forum is for me. Second forum is for you. So I will try not to disturb, interrupt here. So this is for yourself, okay? Then this one is for me. I will answer. I will bring it to the class and answer every week or every day. Every day, okay? Announcement is for me to make announcements. And then I put out some maybe helpful notes for you to refer. Maybe it doesn't make sense now, but later on you can refer back. So every week I'll put out pre-read section for you so that you can just go through the section before the class so that you are not that lost. I'll put out some tutorial question and I will provide some provide solution to these, but we won't discuss all of them in the class. Okay, so I will pick some of them, maybe one or two from each section to discuss in the class. Okay, because we don't have much time to do it. But for you, you still need to do exercise so that you will get acquainted with the concepts. Okay. Yeah, I've already put out some pre-read notes for all the topics that you can go through. So my notes will be based on these notes, and then maybe I'll do some add-on or I just use them. Okay. Yeah. So there are exercises inside these notes, but they are referred to the 5th edition, but it's almost the same as the 6th edition. So you just roughly follow the question number, and then the textbook will provide the odd number solution. Okay, similar to the discrete math course. Okay, so for the discrete math student, so this will be the add-on to the matrix part of the mathematics. Okay, I know that not all of you from maths background, so I try not to be too too formal, okay, in explaining. Okay, but the most important thing in the course is to understand the concept and then understand examples and then able to do calculation. That's all. Okay, makes sense? Okay, also that okay, I acknowledge that maths is hard. Okay, but please don't give up. Okay, so maths is very weird. Okay, so if you just stay on the floor, okay, you will never see anything. Okay, only you walk until a certain height, okay, you can see all the beautiful animals. Okay, so please don't stop climbing. Okay, you have all the resources. You can find me, message me, Teams, or email me, or find me in the office hour. Okay, and also I provide a student forum for you to access to all the other students. Okay, you don't need to know the person to answer the question. Answer the question. You just reply. Okay, help each other. Anything? Any other things regarding the admin side before we start? Any question? Okay. Yeah. So the general idea of this course is revolving around algebra and geometry. Okay. So we want to use geometry is something something you can see like line, plane, or maybe circle, or maybe higher dimensional things. Okay. So how are you gonna compute this stuff? Okay, so we want to encode the information into algebra. Okay, this is what we do in linear algebra. And then we will encode it in the form of something, okay, this kind of number. Okay, maybe this number doesn't make sense to you, but we will see. Okay, so in this form, then we can do calculation. In that form, we can only just draw. Okay, makes sense? So this is about the first bit I put on this before the lecture. Okay. Algebra is the offer made by the devil to the mathematician. Okay, so we will dive into the algebra. Any other question? Any questions? Okay, so in this, when you study, right, don't just make notes. Try to listen to what I say. Okay, if you think that the things I say doesn't make sense, you just call out my name. You just say, Seng, hey, what do you mean by that? Okay, yeah. even if it's a silly question, it's very important. Okay, because most of the time we are stuck at the silly question. Okay, so you just call my name and ask me to write bigger or something like that. Okay, just make yourself comfortable. Let's see what I showed. Yeah, even Teams change the position of the button. Oh no. Just do it. Okay, never mind. Okay. So any question before we start? Oh, okay. So be prepared. The heavy line. Okay. So first lecture. Okay. So first lecture we will we'll study the linear equations in linear algebra. Okay. So I continue. Okay. So first we need to study what's a linear equation is. Okay. So what's a linear equation? Okay. For those not familiar with mathematics, so def will means definition. Okay. Usually we will start with a definition. Okay. If you don't understand the definition, that's fine. Okay. But you have to at least understand the example again. Okay. Use examples to understand the definition. And then from there, we will have some theorem to make. We won't prove the theorem, but we need to apply the theorem. Okay. So first, we will define what's a linear equation means. So linear equation, the variables. So inside linear equation, we have variables. Okay. How many many you want, but finally many is an equation. Okay. So you must expect an equal sign inside equation. Okay, such that you can write it in the form of, is it big enough to see the word? Is it big enough? Okay. So a1 x1 plus a2 x2 plus equals to b. Okay. So what's a1 up to an and b? So uh, so we call the ai the coefficient. Okay. a1 up to an. Okay. So they are either complex or real numbers. But mostly we will deal with real numbers in this course. I think so. Okay. So real numbers includes numbers like 1, 0, 2, e, I, and so on. Okay. So if you don't understand the definition, never mind. So let's look at what's the example of a linear equation. So you could have y minus x equals 0. Okay. This is a linear equation. About 2y minus x plus w is also a linear equation. Okay. So we also can have 2y plus z equals to 100. It's also a linear equation. Okay, make sense? Make sense? Okay. Okay. Next. So let's look at why. Let's look at the first example here. Okay. What does it mean by y minus x equals 0? What value of y and x you can take? What number satisfy this equation? Any idea? Any idea? So your y and x live in real number. Okay, meaning you can take number in reals. So what choice you can make? Okay, so for example, y equals to 1, x equals to 1. Okay, so does this satisfy the linear equation? Yes, right, because y minus x equals to y minus 1 equals to 0. Okay, how about y equal to 0.5 and x equal to 0.5? Okay, so you also can take 0.5 minus 0.5 equals to 0. But if you take y equals to 0.6, maybe just take y equal to 1 and x equal to 2, then you get y minus x is equal to minus 1, which is not 0. Okay, so this is not solution to the linear equation. Okay, makes sense. So linear equation capture all the number that satisfy the equation. Okay, make sense? Make sense? Okay, so from here, actually you can see that if you plot it on the real plan, the R2 plan, I think you have learned this in high school before, right? If you plot out the function, this is the, let me draw it again. This is the y equal to x line, okay? Where this point correspond to x equal to y. For example, this is one. Okay, make sense? Okay. So in geometry, right? So you can have different line, right? If you consider a different line, okay, by changing the gradient or the y-intercept, okay, you can draw two lines on the uh, same plane, right? Okay, so example, also for example, on a plane, you can have two lines not intersecting. Okay, you also can have two lines intersect at one point. Okay, and you also can have two line intersect at every point. Okay, so for example, in this case, we can have y equal to x, 2y equals to minus 2y minus 2y equal to x. Okay, so wait, sorry. So y equal to x and then 2y equal to 2x. So they both represent the same line. Okay. So geometry, we can see intersection point, but what does it mean in the algebra side? Okay. So the question is, what if we want to solve one or more linear equations with the same variables? Okay. So for one variables, we can try and test. So how about two or more? Okay, one or more. So which is a system of linear equations. Okay, how to solve one or more linear equation. Okay, so for example, the solution that find the solution that satisfy these two uh, linear equations. Okay, so what can you do? How do you solve the system of linear equation? Anyone can recall from high school? Anyone can recall from high school? So what do you do? So you set the first one as the equation 1, and then you set the second one as equation 2, right? And then what you can do depends on people, but I will do 2 minus 1 first. Okay, so what I do is you take the whole equation and then take away the first equation. Okay, so size I put like this. Okay, so what you get is minus x minus y equal to 0, right? And then from here, you found that x is equal to minus 1, right? And then you set this as a new equation, and then you try to find y. And then what you do is what do you do? You take 1 plus 2. I think it was. Let me try. X. So what you get is y equals to minus 1. Okay, then you find the solution. So what does this mean? So this means that y equals to 1, x equals to 1, solve these two solutions. So if you try and plot the graph up, okay. So the first one will correspond to y equal to x, and then the second one would correspond to 2x plus 1, right? Okay, so one is y equal to x, and then the second one will be y equals to x plus 1. Okay, and then they intersect at the minus 1. Okay, so which is the second case here. Okay, so from geometry, we can see 3 cases, and then we want to see it on the algebra side as well. Okay, so the upshot here is a system of linear equation has either no solution. Okay, in this case, they don't intersect. Okay, so in this case, they don't intersect. Here, no solution. Okay, or exactly one solution, which we see just now. One solution. Or 3, infinitely many solutions. Okay, these are the 3 cases. So in first cases, we will say that the system is inconsistent. Okay, because they are inconsistent, so they never meet. Okay. And then if it has solution, we'll call that the system is consistent. Okay. So consistent have 2 possibilities. Either it has one solution, or there's no solution. There's a lot of solution. No solution means the system is inconsistent. Okay, makes sense. Okay, good. See some of you nodding head. Okay, so some observation here. Okay, some observation here. It goes to here. So there are some elementary equation operation that we can do when we are solving the linear equation. Okay, so what we can do first is to interchange two equation. Okay, so for example, just now we have this example here. So let's say we have a solution that solve these two equations. Okay, is it the same as I just interchange the two equation here? It's the same system, right? Okay, so we can just interchange the two equations. Secondly, we can also scale all entries in a equation by a non-zero constant. Okay, so for example, if it solve y equal to x, okay, if the solution solve y equal to x, does it solve, for example, 2y equal to 2x? Does it solve it? Yes, right. Okay, because from algebra you can see that the 2 will cancel. Okay, and then thirdly, not really obvious but not too hard to see as well, you can replace one row by the sum of itself and a multiple of another equation. Okay, but this is what we are doing just now. So what we did just now is we take equation 2 plus minus 1 times equation 1. Okay, so we replace one row. We replace which row? We replace row 2 by the sum of row 2 and minus of row 1. Okay, make sense? So this is the operation you can do. So these are the three operations that we can do that we such that we don't change our system of linear equation. Okay, make sense? Okay. Okay. So what's surprising here is really what matters is actually the coefficient of in the system of linear equation. Okay. So what's changing is the number or the constant in front of the variable. Are you comfortable? Am I talking about coefficient and variable? Is it clear? So these are the variable yx, and then the constant in front the variable we call it a coefficient. Okay. Okay. So really what matters is the coefficients in the system of linear equation. Okay. So let's find a way to extract this coefficient out. So let's try another example again. Okay. So let's try another example. Say we want to solve x1 minus 5x2 equals to 1, 3x1 minus 7x2 equal to 5. Okay, so how about I give you 2 minutes, see if you can solve this. Try and solve this system of linear equation. I give you 2 minutes. Try if you can solve it. See if you can solve this. Try use the tree operation that we mentioned just now, and then try to solve the system of linear equation. Anyone try already? So the strategy is to eliminate the variables. Okay. So can you construct a new equation such that x1 is eliminated? So what I do is I take the second equation and take away 3 times the equation. Okay. So what do I get in the end? Take away 3 times the first equation, I get 15x squared minus 3 plus times minus 5. And then minus 3 times 1, I get minus 3. And then I add up these two equations. What I get is 8x squared equals to 2. Okay. And then from here, I get that x squared equals to 1 over 4. Okay. Follow? Okay. So from here, I can set this as a new equation. And then what I do is I take 1 and then add to 5 times 3. Okay. So what I get is x1 minus 5x2 equals to 1. Okay. Plus 5 times 3, what's that? So 5x squared equals to 5. I get is x1 equals to 9 over 4. See, too small, cannot see. Let me move it. Okay, so let me get this x1 equals to 8 over 9 over. Yeah, makes sense. Okay, so you can check your answer. Okay, so check your answer. Okay, so check your answer. So you can do the checking. So let me copy it down. So what I put here is so 9x1 equals to 9 over 4. and then x2 equals 1 over 4. So the yes equal. Okay, so you can do the checking. Okay, so how to do the checking? So you just put your number in, see if the equation is true or false. Right. Okay, is it true? So we can try and do the calculation. So 9 minus 5, you get 9 minus 5. What's 9 minus 5? What's 9 minus 5? Wait, you don't do calculation. 9 minus 5. What's 9 minus 5? 4. Okay. So you get 4 over 4, which is 1. Good. Okay. So how about the other one? So you get 27 over 4 minus 7 over 4. So 27 minus 7 is what? 20. Okay. 20 over 4 is 5. Oh, okay. So work out. Okay. So the magic, the real magic is actually here. So let us put them nicely so that you can see what is going on. Okay, maybe we just put a new page first. Okay, and it's now. Okay, so from here you can actually see that somehow this variable is not doing much work, but the number is keep changing. Okay, so we want to find a way to include all the numbers. Okay, so what we do is we replace this using a what we call an augmented matrix. Okay, so augmented matrix will record the coefficient and also the b. Okay, so in a moment I will tell you how to read this matrix here. Okay, so on this column here, okay, so this column is the coefficient of x1. Okay, you can see that here is 1 times x1 and then 3 times x1. Okay, so this will go into this column, and then second, the coefficient of x2 will go into the second column. Okay, and then the equal sign here, my practice is to put a line. Okay, put a line here. Okay, in the textbook you will see that there's no line there, but to differentiate with a normal matrix, my practice is to put a line. Okay, so that you know it represents this equal sign here, so that this 1, 5 will be split up from the other coefficient. Okay, and then what I can do here, okay, so the magic is here. So just now we get rid of x1, right? So we want to try to get rid of these 3 here. Okay, so what I do is, okay, first I should label this as R1 and R2. Okay, row 1 and row 2. Row 1 and row 2. Make sense? Okay, so row 1 and row 2. So what I do is I take row 2 minus 3 row 1. Okay, so what do you get for new row 2? When I change, okay, typically when I do the, I will write the row that I want to change first. Okay, I'll take R2 minus 3 R1 so that I get a new row here. Okay, so what do I get? I get 0, and then what do I get here? minus 7 plus 15 is 8. And then 5 minus 3 is 2. Okay. So I take the row 2 minus 3 times row 1. Then I get a new row 2. Okay. So this 0, 8, 2 is similar to what I get here. And can see the connection or not? Can see the connection? Anyone cannot see a connection? Anyone cannot see a connection? This part will be very important for this chapter. Okay. So if you can't see the connection, you should ask. Okay, then what do I do next? Is I try to do what? So I try to make this part here 0. Okay, so this is what I do here, right? So I try to eliminate S2. Okay, I also want to try to eliminate this part here. So what I do is I take row 1. Okay, maybe okay. Yeah. Okay, so maybe we reduce row 2 first. So we do 1 over 8 row. Okay. Row 2 divided by 8. So what we get is 1, 1, and 1 over 4. Okay, so this is what we did here. Right? Okay, good. And then next, what we can do is we can follow the algebra part. What we do next, precise. The next step we do is 1 row 1 plus 5 row 2. Okay. So what we get is 1, 0, and 9 over 4. Okay. So you can see that the algebra step can be encoded into the matrix. So this is just an example. Maybe you are not familiar, but we will do more exercise to make you feel familiar here. Okay. But okay, so at the end, what we did is let's copy this again. Let's copy it. Okay. Okay, so you can see that in this matrix form, we don't need to write the variable again and again and again and again. Okay, these variable will be represented by the row or by the column. Okay, by the column. So the position of the number will remember x1 and x2. You don't need to keep writing x1, x2, x1, x2 again. Okay, so from this matrix, you can get these answers. Okay, I'm not precise yet, but the following chapter section we will say more precise the right language. Okay, for now you just see that there's some connection between them. Okay, you should see some connection, and then we will make precise on this notion again. Okay, so what we do here is we replace the elementary equation here become a elementary rows equation. Okay, so you are free to interchange 2 rows in the matrix. Okay, so we're in augmented matrix. Okay, and then you are free to scale all the entry in a row. Okay, so this is what we did just now. We scale a row. Okay, and we can replace the row by the sum of another row. Okay, so instead of writing the equation, we just care about the augmented matrix. Okay, the coefficient plus the B, the solution. Okay, so to go to the next part, there's two question we need to think about. So 2 questions we think about here is, let me see, where's the, okay. 2 questions we think about here is, given a system, is the system consistent or not? Do we have a solution? Yeah. If you have a solution, is it unique? Okay. So this is the existence and uniqueness question we should think about. So do you want to have a rest first, or you want to do question first? Which, huh? Do question first? Okay. So let's spend, okay. So when we go into a tutorial question, I hope there's someone sitting beside you. Can you now, I want you to talk to the person beside you, know their names. Now, 1 minute. Talk to the people beside you or behind you or in front of you. Yeah, because I want you to discuss the question together later. Yeah, try to know the person in front of you, at the back of you, while beside you. Okay. So I have 2 questions here. Okay. Similar flavor. So try spend about 5 minutes solve with your friends together. Okay. So try 5 minutes and solve it. And then after that, I will spend 5 minutes explain it. Okay. Try discuss with your friend and then do these 2 questions here. You can discuss with your friend, okay? Yeah, try solve it. Try give me the x1, x2, the solution to me later after 5 minutes. You can use algebra way. You also can use matrix way. Okay, you can try both way for now, and then try and see the similarity. If you can't see it, it's in the textbook 1.1. Question 2 and 12. It's in the PDF. Anyone can finish, can shout out the answer and check. You want finish and shout the answer and then we can check. Okay, anything, everyone? Yeah, what do you get? Mm-hmm. Mm-hmm. This one equal to 12, and then minus what? 7. Okay. Yep. Okay, this is correct. Okay. You done 12? Yeah. Next one before. X3. 3. 4, 2, 3. 3? 3, right? 3. Okay. Hmm? S3. Is it 3? 3? 3. Oh, 3. Okay. It's 3. Okay. 3. So it's 3. Okay. Let me see. This one equals to 3. 3. Okay. What I get is 0, I think. Not sure if I'm wrong or not. Okay. But let's discuss. Okay. So let's try and do this one. Not too sure yet. So put a box. Let us check together. Okay. So what methods you all use? Do you use the algebra method or the matrix method? Matrix. Okay. Some of you use matrix. You cannot move it again. Okay, never mind. I'll copy it. Let's see. So, okay. So what's the question 2 is? So question 2 is 2x1 plus 4x2 equals to minus 4. 5x1 plus 7x2 equal to 1, equal to 11. Okay. So, do you want me to show both method or not? You want to start with the algebra method or you want to start with a matrix method? Huh? Matrix. Okay. So you guys are okay with the algebra. So let's do the matrix method. Okay. Why the door keep moving now? Okay. So what you do is you turn this into a augmented matrix. Okay. So let me repeat again. So this is an augmented matrix. How you obtain it is you write your equation in the form of variable equal to a constant first, and then you read out the coefficient, okay, and then you put a line to denote the equal sign, and then you will put the constant on the right of the line. Okay, so this is how you get the augmented matrix. Everyone is okay with this? So this is the basic skill for this topic here. So replace linear system with a augmented matrix. Okay, what you do next is we want to eliminate one variable from one row, right? So what I will do is you do row 2. I do like, let me see what is the quickest way. Okay, so first line can be scale, right? So because everything can be divided by 2, so I'll divide by 2 first. I'll make it 1 easier for calculation. So 1, 2, minus 2, 5, 7, 11. Okay, so I can scale one row. This is the one of the elementary row operation. I can scale a row without changing the solution. And then what I can do next? What can I do next? I can take row 2 minus 5 row 1. Okay, so what I get is what? 5 minus 5 is 0. 7 minus 5 times 2 is minus 3. Is it? 7 minus 5 times 2. And then 11 minus 5 times minus 2, you get 21. Okay, you get 21. Okay, so what can you do next? I think I can scale first so that I make entries into 1 again for easy calculation. So I scale the second row first. I get 1 and then minus 7. Okay, and then I try to eliminate this term again. Okay, so what I do is 1 minus row 2 times row 2. 2 minus 2 is 0. Minus 2 plus 17, 14 is 12. Okay. So from here we can see that x1. I think I skipped something. I'm not sure you notice or not. So I can go from this matrix to let me draw it again. So I can go from this matrix to equation again, right? So this put back to the equation, I get 0 times x1 plus 1 times x2 equals to minus 3, which is equivalent to x1 equals to 12 and x2 equals to minus 7. Okay, so there's nothing mystery here. So I just put the augmented matrix back to linear equation. Okay, make sense? Make sense? Okay, make sense? Okay. So when you do this matrix, right? So inside your mind, you should have this linear equation line inside, line at the back. Okay. So you have some x1, x2 here. Okay, just that we ignore it because we already know that it is the coefficient belong to belong to some xi. Okay, because based on the column that leave. Okay, based on the column that leave, we will know that which coefficient is it. Okay, so we can freely go from matrix and then back to linear equation. Understand? Any question on that? No? No? Okay, so what's going on with the 12? If you have done the algebra part, you can try and compare these two. Try compare the algebra method and this matrix method. Okay, algebra meaning the variables, the method of variables. Okay, so let's do one more. Okay, the first lecture we should go a bit slower. So let's do one more. So one more. So this question is minus 3x 2 plus x. Let me see it. 3x1 minus 3x2 plus 7x3 is equal to 8. And minus x1 plus 3x2 plus 2x3. Okay. So turn it into the augmented matrix. What do you have? First row, what do you have? What's the coefficient? You tell me. First row. What's the coefficient? Huh? 1, 3, 4. Okay. And then the constant is minus 4. How about second row? 3, 7, 7, minus 8. Okay. Next. Minus 4, 6, 2, 4. Okay, good. So you got this. So what you should do? What you should do is to make, you just want x1, s2, s3, right? So you need to make this 0. Okay, so make all these 0 and then you will get your solution x1, x2, s3, s2, s3. Okay, so what can you do first? What do you do first? What I do is I take row 2 minus 3 times row 1. Okay, so my convention is I put the row that I want to change first. Okay, so if you look, you will see my working here, R2 minus 3 times row 1. That means I'm replacing R2. Okay, because similarly, I also can write minus 3 times row 1 plus row 2. This is the same. You will get the same row, but now is the method where you put the row. Okay, so my convention is the row that I want to change, I will write it first. Okay, so since I wrote R2 first, I'll change row 2. Okay, so I'll keep row 1. Change row 2. So 3 minus 3 is 0. Minus 3 plus 9 is 2. 7 minus 3 is minus 5. So minus 8 plus 12 is 4. Okay. Keep the rest. Okay, so do one operation at once. Next, you will see that I will do R3 plus 4R1. Can anyone do some speed calculation for me? You get first must be 0 because that's what my purpose is. How about second one? -6. Third one? 10? 10? 10? 10 or 8? 10 or 8? 18. Okay, correct, 18. Oh, I see my mistake already. Okay, then 4 minus 16 is -12. Right? Okay. Okay. I think I see my mistake. Okay. How about the next one? What do I do? Want to scale first or just do it? Okay, just do it. Too lazy to scale. Okay. R3 plus 3R2. What do you get? Can someone help do the calculation? 0, 0. And then what do you get here? 3. 3. Help me check. Is it 3? And then -1. Someone say -1. 0. Okay, 0. Yeah, correct. 0. 3. Is it 3 here? Is this 3? 3, right? Okay. Okay, good. Okay, next one, I want to get rid of -5. What do you do? So I do, maybe I scale first. I scale R3. 4 -4, 0, 5 -5, 4, 0, 0, 1, 0. Okay, I scale this one. And then next, what I do is I want to get rid of -5. So I need to take R2 and then plus 5R3. Okay, based on R3 I do. Okay, so what do I get? I get 2, 0, 4 minus 4, 0, 0, 1, 0. Okay, make sense? Following? Okay, following next. I want to make this one 0 again. So R2, R1 minus 4, R3. Okay, so what do I get is 4 minus 4, 0. Minus 4 minus 0, still the same. Minus 4. Okay. And then next we get, let's scale the second row first. Okay, so that it's easier to calculate later. So what we get is 1, 0, 2. 0, 1, 0, 2. Okay. And then we want to get rid of -3 as well. Okay. So what we do is, are you coming into the right course? Maybe. We started 1 hour ago. Okay. First day got people into the wrong classroom. Okay, so next we want to get rid of this one. So that we're left with x1. So r1 plus 3r2. Okay, and then we get 0, 0. And then what's the constant term we get? Is 2. Is it 2? 2, right? Okay. So that's 2. Okay, is this the right answer? We need to check. Put it back into this solution and check. Maybe I'm wrong, okay? I don't know. I need to check. Everyone make mistake, right? So let's see. So we need to check. Let's check. So from here, just now we see that this is equivalent to what? x1 equal to 2, x2 equal to 2, x3 equal to 0. Okay, make sense? Everyone got this or not? Do I need to repeat again? I think I repeat again. Okay, so from this augmented matrix, we have 3 equation here because we have 3 rows. So these are the coefficient for the variable. Right. So 0 will eliminate the variable that you don't need. Okay. So from these 3 equation, we will get x1 equals to 2, s2 equal to 2, s3 equal to 0. Then let us move this down further. So we get x1 equals to 2, x2 equals to 2, s3 equals to 0. Okay, let's see. So if I put 2 here, 2 minus 6 plus 4, something wrong, is it? So where is the mistake? Eh? Anything wrong here? Minus 2 minus 6 plus 4 is 0. Something's wrong, is it? No, nothing wrong. Nothing wrong. Let me try. Oh, because it's 0. Okay. So let me move it up, write it up. I thought it's 1. Okay. 2 minus 3 times 2 plus 0 is equal to minus 4. Okay. And then how about this? 3 times 2 is 6. 6 minus 7 times 2 is minus 8. Minus 8 plus 0 is minus 8. Okay. And then minus 4 times 2 is minus 8. Minus 8 plus 12 is 4. 4 plus 0 is 4. Okay, good. So every time you should do the checking. Okay. Any question? Any question or not? Any question? No? Okay, let's take a break. We come back at 4:24. Okay, 4:24. We continue to 4:24.
I just have this. No.
What are you trying to do? One. So what do you
So I replace row one. It's this one.
Okay, you put R1 equals to
为什么这边这么是错的？
这个。哦，没有。I do this. Actually, I replace R2, not R1. 啊，没有动。
对，我也不知道
因为
有啊，
为什么我要？你也可以用 R1。
但是 R1 它不是做回来后面就很奇怪。
你看啊，你看。如果你要 replace R1 的话，有什么这样？后面做起来很奇怪，不应该要奇怪？给我看一下，给我看一下什么出问题？不应该要奇怪？给我看一下，你讲如果你 replace R1 的话，然后你现在要做的事情是你用3个R2减掉7个 ，OK？ 对，355对，我就对33加30 33
哦，
呀，也是可以的，但是呀，是33。所以看一下，如果我换去33是180，OK？所以你第一个你就拿到减7，第二个你拿到什么？ 12一样的对 x1 的一样的，不可能有问题的。嗯，然后你要 make sure 这样子啊，你要可以啊，也可以啊，
那个
可以。但是哦，你如果这样子写，不是通常啊，我们会分辨一下这两个 R1，所以我们会放一个 star 那边 new R1。
以
好，
前
你们老师
以
讲
前那个过全用的时候不用
谁呀？
全用。
谁是全用？哦，全用哈。
嗯，
我学的时候是要啦，而且啦，从数学的角度来看啦，因为这两个是不同的东西，所以我就没有教你们写这个东西，我只是教你们写步骤出来就可以，然后要记得自己在 replace 哪一个。
对，那以前
有些啊，对，不，我是说如果这样写的话，我是说最好写一个这样来记一下，这是一个新的东西，OK 吗？全用看
对啊，全用
什么课哦？
engineering mathematics
做 engineering 啊，OK，可以可以，
当时学的时候，他就叫我们要把这个写出来。
再把这种 OK。哎，
啊，这种没有。
是问写的问题，如果我这样，我会不会糟糕？
要写那个刚才我写的那个东西，
就是要写这种格式，
至少要把这个写出来，就是你怎样从这里去这里，这里去。
就像这样是要扣分的，
嗯，
变的比正面的合作。
第三吧，
对，
会，等一下我再说一次， Yeah. Okay, before we start, the tutorial, the lecture notes, I will post two versions after the class. So one version is everything on board, I'll post it. Even with mistake, I'll post it so that you can refer to the mistake and then ask. Second is I will check all the mistake and then I check all the format I want. I will pull out a fine-tune one. That one will be later, okay? The in class one will be pretty soon, but the fine-tune one will be later. And then yeah. So there are two versions. Every day I will post it up after the lecture. Okay, one is the in-class one with mistake if there's any, and second one will be a fine-tuned one. No mistake. But any mistake, you should refer back to me again. And now I will pass down the attendance sheets. Okay, please sign and then take care of it because you need to stay for 5 weeks. And then please don't sign for your friends. Your friends who are absent, they should email me. Ask your friend to email me if they can't make it to the class. Okay. Okay, there's one student just now asked me if I can write something like, let's say, if I replace R2, I can put R2 here. And if I replace R3, can I put R3 equal to this? Okay. And so you just write an extra row to record which row you change. The answer is yes. Okay, you can do this, but I suggest you to put a star on the new row. Okay, because technically, the row 2 here and the row 2 here is different. Okay, so this is a new row. This is the old row. Yes. In fact, this is what I learned before. Yeah, but I think that we can just throw it away, so I don't bother it. Okay. So if you want to do this, make sure you label it as a new thing. So you can put a star to differentiate the new R2 and the old R2. Okay. Otherwise, I will base on the first row you write, then you will replace the row. Okay. The first row you write, you're replacing the row that you want to replace. Okay. So anything you want to do is fine as long as you state it clearly inside your solution. Okay, but without this, I think it's very hard to know what you're doing. Okay, so make sure you write out the step. Okay. Okay. Next. Okay. So what we are doing just now is actually finding the row echelon form. Okay. So first of all, what does the echelon mean? Okay. So echelon means step like. Okay. Step like. Okay. It's like what I draw just now is like a step. Okay. So what's a step like about? Matter inside matrix. Okay. So a rectangular matrix is in echelon form or row echelon form. Okay. If it has the following three properties. Okay. So first property is all the non-zero rows are above any row of zeros. So how do you picture this? Let me make bigger. So how you picture this? So all the rows of zero must be below any non-zero rows. Okay, this is what it means. Something like this. Okay. So you cannot have something like row of 0 at the top and then something like this. Okay, this is what you cannot. Okay, all the rows of 0 must be at the bottom. Each leading entry of a row is in a column to the right of the leading entry of the row above it. So what does it mean by a leading entry? Okay, so let's define this leading entry first. So let's define this. So the leading entry is the leftmost non-zero entry in a non-zero row. Okay, so for example, this one is a leading entry. Okay, I put LE here. And then this one is a leading entry. Okay. Row of 0 has no leading entry because it's not non-zero row. And this one is a leading entry. Okay, it's a leftmost non-zero entry. And then it says that each leading entry of a row is in a column to the right of the leading entry of the row above it. Okay, so what does this mean? How to picture this? So to picture this, you should imagine something like this. Okay, so let's take a 3 times 3. So for example, like this. Okay, so each leading entry is in a column to the right of the leading entry of the row above it. Is it the right English or not? To the right of the leading entry of the row below it, right? To be below this one. Okay, so to the right of the leading entry below it. Okay, so you cannot have something like 0, 1, 0, 1, 0, 0, 0, 0, 0. Okay, this one you cannot have. Okay, put a cross, put a big cross. Okay, so each leading entry of a row is in a column to the right of the leading entry of the row below it. Okay, so you also could have something like this. 0, 0, 1. Okay, so it's to the right of the leading entry below it. Make sense? Make sense? Okay. Okay. If not, you should point out. All entries in a column below a leading entry are 0. Okay. So in this case, you can see that under the leading entry, these are 0. Under the leading entry, these are 0. Under the leading entry, these are 0. Okay. So you could have something like this, but you cannot have something like this. Okay. So because you have a non-zero entry below the leading entry. Okay. If this is a leading entry, below it must be 0. Okay. So I need to satisfy these 3 conditions here. Okay, doesn't matter. Later we will see example again, and to make you visualize what this 3 property is. And then if the leading entry is 1, okay, we call it a reduced echelon form or reduced row echelon form. Okay, if the leading entry is 1, and then 1 is the only non-zero entry in its column, then we call it a reduced echelon form. Okay, so let's look at example. Okay, so keep this definition in mind and then try to verify it using examples. So let's see. So it claims that these matrices are in echelon form. Okay, so let's check why are they in the echelon form. So first is all non-zero rows are above any rows of 0. Okay, so you can see that all the non-zero rows is above the row of 0. Okay, all the row of 0 is at the bottom. And then each leading entry of a row is in a column to the right of the leading entry of the row below it. Okay, so you can see that this there's a step here. Okay, so now you can build the step. Okay, this is the reason of point 2. So from point 2 you can build the step. Okay, and then all entries in the column below are 0. So you can see that below this leading entry is 0, below this leading entry is 0, below this leading entry is 0. Okay, and so on. Okay, so this is the echelon form. Okay, but these two are not the reduced row echelon form. Okay, first of all, we don't know the leading entry is 1 or not. Okay, we need to make sure it is 1. Second of all, inside the column of leading entry, other than the 1, they have to be 0. Okay, meaning this part have to be 0, all these part have to be 0, and then above the 1 have to be 0. So meaning the top and the bottom of the leading entry must be 0. Okay, so you can see there's a star here. Star means you can put any number here. Okay, any number allowed. You can put 0 or you can put 1 or put 2, anything. Okay, but 0 is only 0. Okay, so we can see that to make these two into a reduced row echelon form, we need to replace the leading entry by 1. Okay, scale it by 1. And then we need to make anything above 1 be 0. Okay, can see it? Okay. Any question on that? Make sense? Any question? So reduce row echelon form, you need to make your leading entry to be 1 and then make anything above 1 to be 0. Okay, below 1 is always 0 by the echelon form. Okay, and then anything above 1 you need to make it 0 to get reduced echelon form. Is it too fast or not? Any question? Any question? No? Okay, so let's go back here. So is this reduced echelon form or a reduced raw echelon form or raw echelon form? This one. Reduce. Okay, so this is both reduced and echelon form, because to be a reduced raw echelon form, you need to be a raw echelon form first. But this is a reduced raw echelon form because the leading entry is 1. All leading entry is 1, and then anything above 1 is 0. Okay. Okay. Let's pick another one. Is this matrix a raw echelon form or reduced raw echelon form? Raw. Okay, raw echelon form, because you have the leading entry and then everything below the leading entry is 0. Okay, so you can see the step. Okay. How about which one? Which one is better? Okay, that's all. Okay, never mind. That's all. Yeah. Okay. So one question you can ask is, what are the possible reduced row echelon form for matrices of different size? Okay. For example, let me see what we want to do with this. Okay, for example, in the 2 times 2 case, Okay, we could have 1 on the first column and then 0 in the second row. And then we could have anything here. Okay, we also can have 0. Okay, this is one reduced row echelon form we can have. And then we also can have 1, 0, 0, 1. Okay. We also can have 0, 1, 0, 0. Okay. So these are the 3 reduced row echelon form that we can have on the 2 times 2 matrix. Okay. 2 times 2 means 2 rows and 2 columns. Okay. Next week we will give the definition, full definition. But for now, when we say 2 times m times n or 2 times 2, it means 2 rows times 2 columns. Okay. So how about 3 times 3? Okay. Try figure out how many possible reduced row echelon form you can have for 3 times 3, meaning you have 3 rows and 3 columns. How many possible reduced row echelon form you can have? I give you 2 minutes. Try and figure out how many reduced row echelon form you can draw for 3 times 3. Yes. You can discuss with your friend as well. After you try, you can shout out the number, how many possible reduced row echelon form. Anyone get it? Anyone? How many possible reduced row echelon form you can draw? Anyone? Anyone try? Or give me some example of reduced row echelon form for 3 times 3 matrix. Anyone try? You can tell me the entry, please. Anyone try? Just give me any. Anyone try? Have you tried? Sorry. 7. Okay, can you tell me the 7 matrices that you draw? Okay, tell me like what's the first one? 0, 0, 1? Huh? 0, 0, 0, and then 0, 0, 0. Okay, good. So under the leading entry, you have all 0. Okay. And then what else? 0, 1, 0. All 0. You mean all 0. Okay. What else? 1, 0, 0. All 0. Okay. What else? 0, 1. Huh? star. Okay. And then all zero. All zero. Okay. Huh? Which one? Yeah, if so can you speak louder? Okay, so which one you want to change? Huh? Which one you want to change? Which one? Fourth one. Okay. This one. 100. 001. And then 000. Okay. And then 100. 010. 000. Okay. About the last two. 010. Okay. 001. 30. Okay. That was the last one. 100. 010. 00. Okay. So let's check. So we already checked the first one. This one okay. How about this one? Okay. So this one actually we allow here to be star. Okay. So we can put anything after 1. Okay. Similarly for this one, we can put anything after 1. Okay. And for the fourth one, we can put anything for the second 0, but not the third 0, because anything above and below 1 have to be 0. Okay. Anything above 1 and above and below 1 have to be 0. So similarly for this one, we can put anything here and anything here. Okay. And then that's all. Okay. Yeah. So this is the 7 matrix, 7 type of raw reduced echelon form we have for 3x3. So why is this important? Because this is important for your calculation. I think mostly we will deal with 3x3. If not, you need to take care. So why we care about this row echelon form is there's a theorem says that, let me make it bigger. So each matrices, each matrix is row equivalent to 1 and only reduced row echelon form. Okay, so row equivalence meaning after applying sequences of elementary row operation. Can I do short form? Okay, elementary row operation. So you can do interchange, you can do the scale, you can do replacement. Okay, and then you will finally reach to only one unique reduced row echelon form. Okay, this is the calculation we did in the first hour. Okay, so we do all the calculation and then we stop at one reduced row echelon form. Okay, so this is a theorem. That's why we are care about this reduced row echelon. Every matrix we can reduce it using the 3 operation to a reduced row echelon. Okay, make sense? Okay. So before we go into row reduced algorithm first, before that, let's come back here. So when the leading entry is 1, we will call it a call this a pivot column, the pivot position. Okay. So pivot position is So pivot position is leading and is the leading entry. It's the leading entry, which is 1. Okay, so we will say that these are the pivot position. Yeah. Okay, so these are the pivot position. So when they are 1, we call it a pivot position. Okay. And then the column is lies in, we will call it a pivot column. Pivot column. The column that have a pivot, we call it a pivot column. So let me draw the highlight. Okay, let me highlight the pivot column. So highlight the pivot column. Okay, so you can see that inside the pivot column of a row, a reduced row echelon form, above the pivot position and below the pivot position is 0. You can see it. Okay. Inside the pivot column, the only non-zero term is the pivot position, which is 1. Can see it? Everyone can see it? Inside the pivot column, the only non-zero term is the pivot position, which is 1. Okay, so above and below 1 have to be 0, so that you get a reduced row echelon form. Okay, reduced row echelon form is what we're looking for the solution. Okay, we will come back to this again. Okay, so let's discuss about row reduced echelon, row reduction algorithm. Actually, we already encountered this in the first hour, so now we make it precise. Let's see what we want to do. Okay, let's use this example then. Okay, I will illustrate it using this example here. Let's reduce this matrix 0, 2, 0. Okay, make it bigger. 0, 1, 2, 0, 2, 0, 2, 0, 2, 0, 2, 4, 0. Okay, so what I want to do is I need to find. Okay, let me describe the algorithm here. Have everyone signed the attendance list? Everyone signed? You. Okay, so algorithm first is to find a possible pivot position from leftmost non-zero column. Okay, so you can see that the leftmost column is the first column here. Okay, there's a non-zero term here, but it's not at the top yet. Okay, because we want to do the step like, right? Okay, so we cannot have something like this. Okay, in this case, you will drop. Okay, so you need to do something like this. Sorry. Okay, do something like this. Okay, imagine you are walking up. Okay, so you cannot walk like this. So first, you need to move the non-zero term to the highest position first. So what you do is you can interchange the row, because this is one of the elementary row operation. So what I do is row 1 exchange with row 2. Okay, so what I got is 2, 0, 2, 0, 0, 1, 2, 0, 0, 2, 4, 0. Okay, so first I found a possible pivot position. It's not pivot position yet because it is not 1. Okay, it's just a leading term. Okay, but anyway, we will keep it first. And then we want to find a second pivot position. Oh, wait, sorry. So the second is, before that, we will make 4 entries below the possible pivot position 0, okay, by elementary row operation. Okay, ERO, I just simplified. So you can see that in this case, they are already 0. Okay, you don't need to do anything. So what you do next is you keep finding, okay, keep finding the possible pivot position and then repeat 2 again until all pivot positions are found. Okay. Okay, so second pivot position, which one you want? Row 1 or row 2? Which one you want? Which one you want? You want to keep row 1 or row 2 as your pivot position? Which one you want to pick? Because the leftmost now have 2, you can pick any one. Which one you want to pick? Usually I will pick row 2 from row 2, position from row 2, because later we want to make it a reduced row echelon form, which need the leading entry to be 1. Okay. If I pick the third one, I need to divide by 2 later again. So I don't want to do extra work. So I just pick the one with 1 first. Okay, to be my pivot position. And then I repeat the second step. Make everything below the pivot position, possible pivot position 0. Okay. So what I do is I take row 3 minus 2 row 2. Okay, what do I get? So I get 0, 0, 0. Okay. So is this reduced row echelon form yet? Yes or no? Is this a no? Why? Why? Okay, yeah, because the first leading entry is not 1 yet. Okay, so you need to scale it. So you make it 1, 0, 1, 0, and 0, 1, 2, 0, 0, 0, 0, 0. Okay, so now you check again. Everything below the pivot position is 0. Everything above the 0 position is 0. So this is a reduced row echelon form. So this is a reduced row echelon form. Okay. Yep. Okay. So every time we're solving a linear system, we're looking for a reduced row echelon form. So how to read this solution here? Okay. So next question is how to read the solution from row reduced echelon form. Okay. So just now we already see it, but we haven't make it precise yet. It is called a parametric description of solution set. Okay. So for example, suppose the matrix we consider just now, okay, is an augmented matrix. Okay. So whenever I say augmented matrix, you should automatically change it to linear equation. Okay. So that means you should imagine there's a line here. Okay. And then there's a equation. These are the coefficient of the variables, and then this is one equation. Okay, replace the line with equal. So what you get here, there's 2 rows, non-zero rows here, which correspond to what? Correspond to 2 linear equation. You know which 2? You know which 2 linear equation you can get from this augmented matrix? 1 times x1 plus 0 times x2 plus 2 times x3 equals to 0. Okay, and then 0 times x1 plus 1 times x2 plus 2 times x3 equals to 0. Last one doesn't matter because you can see that you can, if you write it out, it's just 0 and everything is just 0. Okay, so this one doesn't contribute. So what you really get is x1 plus 2x3 equals to 0, and then x2 plus equals to 0. Okay, so from here, how do we interpret the answer? So the general solution is x1 is equal to minus 2x3, x2 is equal to minus 2x3 as well, and x3 is free. Okay, free meaning I need to write down. So meaning it can be any number. Let me write it larger. It can be any numbers. Okay. In this case, we will call the first two the basic variable. And then when it is free, we call it a free variable. Okay. Why is it free? Because there's no condition on S3 here. Okay. You can see that the third row is 0. There's no condition on S3. But x1 and x2 will depend on x3. Okay. This is what it means by the parametric. Okay. So the parameter here is S3. If I change S3, S1, S2 also change. Okay. Make sense? Make sense? Any question? So parametric means the parameter. Okay. So in this case here, the parameter is S3. S3 can be changed freely. Okay. Any question or not? Any question? If not, now it's 5 o'clock. Okay, 5 o'clock. Let me see what we do. Okay, let's do another exercise first to see whether you know what's going on. Okay, let's try and do this. Spend 5 minutes. Try and solve this augmented matrix and then write down the general solution, the parametric description. And discuss with your friends if you want. Yeah, try get this augmented matrix into a raw reduced echelon form. So in your textbook, they will mention whether it's augmented or not. So for me, I will start with the notation like this. Okay, then you try and raw reduce it. So if I say enough. Okay, so row reduce meaning this part here, okay? Row reduce for this part. So let me write down. I see some of you haven't signed. Zoe is here, right? You haven't signed. Zoe signed. Oh, here I haven't signed. Okay. Here. Okay. Anyone try out? Have anyone tried out? What's the general solution? Anyone get the solution yet? Huh? So you got it? Huh? Minus 5, 3, and 3 is 3. Okay. Okay, let's check. So what do you do first? Can you say what do you do? Huh? What do you do? How to row reduce it? Huh? Okay. Okay. How about row 2 minus 2 row 1? Okay. Let's replace row 2. So what do you get? You get 0. And then in this case, you get minus 1. And then in this case, you get 0. And then get minus 3. Is it? Yeah. Okay. Correct. Yep. And then what's the next? You make the row 2 into a pivot column first. So you put minus row 2. So you get 0, 1, 0, 3. Okay. And then you want to make anything above the pivot position to be 0. So you need to make R1 minus 4R2. Okay. So what you get is 0, 0. And then 7 minus 12 is minus 5. Okay. So from here, you can build your equation again. So it's 1 times x1 plus 0 times x2 plus 0 times x3 equal to minus 5. And then 0 times x1 plus times x2 plus 0 times x3 equal to 3, which means x1 equals to minus 5, x2 equals to 3. And S3, there's no condition, so S3 is free. Okay, then you can see that the pivot happens in x1 and x2. Okay, so there's no pivot position here. So if there's no pivot position, then basically the variable is free. Okay, so basic well, let me write down here. So basic variables corresponds to a pivot position. Okay, and it's free. And then is this how I wrote it? Yeah, okay. So this is the general solution. Okay, good. General solution. Okay, any question? Any question? No? If no, let me see. Okay, if no, can we break for 5 minutes because I'm not sure got enough time or not to cover. So let's break for 5 minutes and then we start over. Come back at 5, 1, 3.
对，
3乘3它只有7个吗？
只有7个。
它只有7个吗？
嗯，
我看一下那个笔记，因为我看
有找到多余的还是找到多余？
有啊，就是
看看
这个就
哪个？感觉还不在这个里面。这个在这个，对于这个，对，
这个也就是
哪一个？
这2个是随意的。
这一个，哎，这个，这个，
然后呢，这2个只有这2个的，
这2个是这个。
我它是这样找的，就是
嗯，
那如果只有这边这一个的话，有吗？
这一个，
对，左下角
不可以哦，因为所有零的一定要在最底
是0。
，rows of zero 一定要在 bottom。这个对，就你不可以有零在不是零的上。
就是如果是000的话，只能是最后一行。
对，所有000的都要放到最底。
这个，我就是说我中间这行是0，或者上面这行是0都可以。
不可以，他们一定要移到最深。
就是
对，
所以我就从下面的是0开始找。
对。Okay, okay, let's start. Just now, for this row reduction algorithm, right? I forget to add the step, although I mentioned in the example. So the final step is to make every leading entry 1. Okay. So you check beginning with the rightmost possible pivot position. And then getting smaller. Let me move everything up to make space. Okay, begin with the rightmost possible pivot position and working upward. Okay, so you go up you go down the stairs. Okay, so you go down the stairs. Give you the imagination. So you go down the stairs. Okay. So working outward and to the left. Okay, all the way to the left, top leftmost. Create zeros. Okay, this is what we mentioned just now. We have to map everything above the leading entry zeros. Create zeros above each possible pivot. Okay, and then make for leading entry. Okay, makes sense. Okay, so so in your textbook you will see that these three will be called. Let me change another color. So these three will be called a forward face, and then this one will be called a backward face. Okay, how to imagine the forward and backward? So what you do is you find pivot position. Okay, make 0 below the pivot position. Okay, and then after you find all the pivot position, make everything above the pivot position 0. Okay, starting from the rightmost. So you make here 0 first, and then make everything before it 0. Okay, so forward and then backward. Make sense? Make sense? Question? Any question? Question? No? Make sure you ask. Make sure you ask question. Okay, otherwise get lost easily. So, yeah. Okay, nothing to add. No question? Okay, so this is very important skill for this topic here. Okay. Next is we haven't talked about vector yet. Okay, let's go. Okay, let's talk about vector. So what's a vector to you? I think you have learned vector before, right? So what's a vector to you? What's a vector to you? So a vector in a 2D plane, so we will call it a R2, okay, or a 2D plane, is something coming out from the origin with an arrow, right? Okay, so something like this. Something like that. Okay, so vector. But actually, this vector can be encoded using two figures. Okay, so for example, we can write it as v1, v2. Okay, just by this point here. Okay, the point it points to. Maybe this one we call it A1, A2, and then this one we call it A2, B2. Let's name them. How to name them? Make them V, W, Z. Okay, but we prefer to write it vertically. Okay, so we will write V1, V2 in this case. Okay, but they are equivalent way to represent the vector. But we prefer this. Okay, prefer. Okay. So you could imagine higher dimensional, you can have more. So maybe you can have more numbers here, V1, V2, V3, up to whatever n you want. Okay. So this is a vector in R12 poly. Okay, maybe I don't use this. I say leave in. Okay. So this one leave in R2. Leave in R2. Okay. What's next? So If we have vectors, so we can add vectors together. Okay. So how do we add vectors? So we add them term-wise. So what do I mean by that? So you have to add V1 with W1, V2 with W2. So, okay. So without swapping the position. Okay. So add term-wise. So if they are different size, you cannot add them together. You can only add the same size. Okay. And then second is this is a sum. Second is a scalar multiplication. So which means we can take any number and multiply it. Okay, so how do we multiply? So one side you got one number, the other side you got n number. So what do you do? Multiply every number with the same number. So let's take an example. Okay, so let's say we have a v equals to 1, 2, and then w is equal to -1, 3. Okay, so what is v plus w? What is v plus w? Anyone? What is v plus w? 0 and 5. Okay, good. So for example, 2 times v is 2 and 4. Okay. So yeah. So when it is a vector, we will put an arrow here, okay, to differentiate it with variable. We'll put an arrow for vectors. So we can differentiate vectors and variables. Okay. This one skip. So there's algebraic properties here. Okay. Last semester we already see this a lot of time, right? So if you add u and v is the same as adding v and u. So this is the activity. Okay. And then it is associative. Adding the first two is the same as adding the last two first. Okay. And then third one is the additive identity. You have the zero vector. Okay. When you add everything to the zero vector, you get back yourself. And next is this one is just -1 minus vector. This one is the inverse, I think. Inverse. Okay. The next one, you can distribute your scalar. Distribute. And then third is you can distribute your, okay, the first one is distribute scalar across vectors. The second one is distribute the sum of scalar with your vectors, and then third one is the also associative. This one is a multiplicative. And then the previous one is the additive. Then the last one is the okay. Not very important for this course, but just to show you there's some algebraic structure here. And then later we will see that matrix also has similar algebraic structure. Okay. Now it's just a column, right? Okay. When we look at matrix, they also have the same algebraic properties. Not very important, but can have a look. And then the next concept is this concept is important because we will use it again and again. So which is called the linear combination. Okay. So given n vectors here, okay, the linear combination of them is sum of scalar multiple of these vectors. Okay, you can see that this is the scalar multiple of v1 plus scalar multiple of v2 plus up to scalar multiple of vn. So how to say? So to say this. So for example, let's give an example here before we proceed. Okay, so let's look at v equals to 1, 2 again, and then w equals to -1, 2 again. Okay, so what is the possible linear combination of v and w? Okay, so one way we could take is 2v plus w. Okay, 2v plus w, what do we get? We get 1 and 6. Okay, so we will say that 1, 6 is a linear combination of v and w, right? Because we can write 1, 6 as 2v plus w. Okay. So you can see that this is a linear meaning there's no square involved. Okay, so it's linear. So combination. So you can take multiplication, you also can take summation. Okay, addition, I mean. Okay, so this is the combination. So this is the linear combination. Okay, because there's no square involving here. You cannot square a vector as well. Okay, so it's linear. And then combination meaning you can take addition, you can take scalar multiplication. Okay, you can take scalar multiplication and addition. Okay, why is it called a scalar multiplication, not a vector multiplication? Because you don't know how to multiply these two together. I bet you cannot. Okay, you cannot multiply two vectors together. But we can multiply a number to a vector. Okay, but we can multiply a number to a vector, which is by multiply every number with the same scalar. Okay. Okay, so scalar multiplication and addition of vector. Okay, let's look at this question here. Okay, so what's this question asking? So you have two vectors here. Okay, so determine whether B, another vector, and C can be written as a linear combination of A1 and A2. For the sake of time, so we just do for B first. Okay, so the question is, can we write B equals to, what's the definition? C1, V1. Sorry. In this case, it's A1 plus C2, A2, where C1, C2 are scalars, which is numbers. Scalars means numbers. Okay, scalar, numbers, number few. Okay, so how to solve this? Okay, how to solve this? So we can see that this is 7, 4 minus 3 here. Okay, is equal to C1 of 1 minus 2 minus 5 plus C2. What is C2? C2 plus 2 by 6. Okay, how to solve this? Can we solve this? Can anyone see this is a similar question to the previous? How to see? How to see? How to see? So what you can do is scalar multiplication, right? So C1 minus 2C. Okay, I think I should move this out because I out of space here. So let's move. Please. Away. Okay, good. So here, so how to see is the same question as what we started in the first hour. So first we multiply out the vector. Right. Okay. Scalar multiplication. So I can multiply the scalar into the vector. Okay. So how to add vectors? So first entry, add to the first entry. Second entry, add to the second entry. Okay. So when are the two vectors equal? They have to equal on every entry. Okay. So 7 equals to C1 plus 2C2. 4 equals to minus 2C1 plus 5 equals to C2. And then minus 3 equals to minus. Okay. And then from here, what you can do? What can you do? You got a system of linear equation. What matrix you can get? Augmented matrix. Okay, so what's the augmented matrix in this case here? What's the augmented matrix? The first row. 1, 2, 7, and then minus 2, 5, 4, and then minus 5, 6, minus 3. Okay. Then go and row reduce it. You want to try yourself? You want to try yourself? And then we maybe after that I'll pause and then we will check. So row reduce it, leave it as a homework. So row reduce it, see if you can find C1 and C2. Okay, so row reduce it, see if you can find C1 and C2. Okay, good. So what's next? So now we create a new relation here. Okay, so the relation is here. So we go off the way from where? From here to here. Okay. So matrix have relation with a vector equation. So this will lead to the next section. Right? Everyone see it? Everyone see it? So we have a vector relate to matrix now. Okay. Just now we have only have connection between. We only know the connection here. Okay. From when we start 3 o'clock. Okay. From 3 o'clock we know this. And then just now 4 o'clock we know this. Okay. Now the last hour we have to deal with this direction. Okay. Okay. Any question? Make sense? Any question? Okay. So matrix with vector. Oh, what's a matrix with vector now? Okay. So next part. Okay, next part, the matrix equation. Okay. So as usual, we start with one definition and then we try to dig this definition out. What does it mean? So if A is a matrix, okay, M times N is the size. So I remind you again. Let me write somewhere. So this one, what color should I use better? One refer to the number of rows. Then this one refer to the numbers of column. M times N matrix with columns A1 up to AN. And if X is in Rn, so you should note that M times N should match with Rn. Okay, so this 2N is the same. Then the product of the matrix and the vector is the linear combination of the column of A using the corresponding entries in X as weight. That is this. So what's this? So let's look at one example. Okay, let's look at example what it says. So let's give 3 times 2 matrix. Okay, so 3 means 3 rows and 2 columns. Okay, so let A be something like 2 0 1 0 3 and 0. Okay, so how about X? X must live in R2. Okay, so which means X only have 2 entries. Okay, so maybe we can pick 2 and 3. Okay, so now how do you multiply AX together? Okay, just now I told you that vector cannot multiply together, right? But matrix and vector can match. Okay, how they match together? Using this definition. Okay, so by this definition, you need to split your matrix into column first. Okay, so in this matrix, you have 2 columns. Okay, and then in your vector also have 2 entries. So how to combine 2 columns with 2 entries? Okay, so you just assign 1 to each. Okay, so how do you assign? You assign the first one to the first column and then the second one to the second column. Okay, this is the definition here. First one assigned to the first column, second one assigned to the second column. Okay, first one assigned to the first column. Okay, so make it clearer. Actually, I should better to write this thing out first explicitly. Okay, first one to the first column, second one to the second column. Okay, and then from here you can do right. So what is this? Just scalar multiple. So you multiply the scalar to every number, similar to this, multiply to every number, and then you do the vector addition. So the end product is a vector or a matrix? What's the end product? Is it a vector or a matrix? Huh? Say again. Vector is a vector. Okay. So the end product is a vector. So what's the vector? So the vector is 2 times 1 plus 0 is 2, and then 0 plus 3 is 9. Okay. So this vector actually live in R3. Okay. So you can see that M, let me use a different color. So M times N matrix multiply with a Rn vector, you get a Rm vector. Okay, makes sense? So you multiply with n, you get Rm. Similar in this case, you multiply with R2 vectors, you get R3. Can see it? Everyone see it? Everyone see it? You realize that this vector changed with this vector, the size. Okay, so the size changed by the size of the matrix. Just one observation. Okay. Okay. Okay, just now we already see that. We see it. Okay, so what's next? So let's look at the example again. So we have a different way to think about the similar question we started just now. So just now we started with y equal to x and y equal to 2x plus 1, right? Remember we have these two line intersecting, okay, at the -1 point. Okay, these two line here. So from here we got a linear system of linear equation, right? And then in this case, we can turn it into a vector form. Okay. So how to turn it into a vector form? We can make the notation compact, become vector. Make sense? Okay. And then we can split up into a vector equation, which is y times. Okay, maybe I do it slower. So y, this one I use plus or minus. Okay, use plus x or minus 2x 0, 1. Okay, and then you can reverse engineer, and then you get y times 1, 1 plus x times -1 minus 2 equals to 0, 1. Okay, so this is called the vector equation. Okay, and from what we learned just now, okay, from what we learned just now, we also can write this thing as what? We can combine the column, okay, and then make yx a vector. Okay, this is the definition of okay, I should put, so I'll put this one. Okay, let me write it explicitly, where w bar is equal to yx and b bar is equal to 0. And then this one is by definition. Let me write it clearly so that you don't confuse. Matrix vector multiplication. Okay. Okay. So these are all equivalent. Okay, so what's next? 543. Maybe I let you see one example and then we deduce one theorem. One very useful theorem. Yeah, any question on this one? This is giving you different way of looking at the same problem, but sometimes one way is easier than the other way, especially when you want to do it on computer. Okay, you just need to input numbers. Okay, let's look at these examples here. Okay, and then we want to observe and then state one theorem. So you have a matrix, you have a vector. Okay, so is the equation ax equal to b consistent for all possible b1, b2, and b3? Okay, so why can they use consistent in this case? We never talk about vector being consistent. So what does it mean? What does it mean to be consistent as a vector equation? Huh? How can a vector equation consistent? Any idea? Any idea? Any idea? What does it mean to be consistent here? Any idea? Sing on any idea? Whoever look at me or call your name. So how is a vector equation consistent? We know that a system of linear equation consistent, right? Okay. But just now I already told you that we can convert a vector equation into a system of linear equation. Remember? So from the vector equation, okay, we can convert into the system of linear equation. Okay, so from here, we can ask whether the system is consistent or not. And then to solve it, we can use the augmented matrix. You see it? Okay, so this connection, this triangle is very important. Okay, from vector equation, you go to system of linear equation, system of linear equation, and then you go to augmented matrix, and then you go around. So everything is equivalent. Okay, make sense? Okay, so try to convince yourself. Okay. Okay, next is okay. We want to solve this. So what does this mean here? So what's the augmented matrix in this case? What's the augmented matrix in this case here? Okay, so I want to solve this, and then what does this mean? This is this 3, 4 minus 4, 2 minus 6 minus 3 minus 2 minus 7 x1 x2 x3 b2 b3. Okay, so maybe to make you feel more comfortable, I write out all the steps. So what's the definition of matrix vector multiplication? So you match every entries to one column, right? Is that what we defined just now? So let's check the definition again. So what we get from the matrix vector multiplication is x1 times the first column vectors plus x2 times the second column vector, and then S3 times the third column vector equals to B1, B2. Okay, has everyone got this? Everyone got this? Okay. And then the next part is you can combine them together again. Be redundant. Okay, so you get x1 plus x3 times x2 plus 4 times x3 minus 4 times x1 plus 2 times x2 minus 6 times x3 minus 3 times x1 plus, minus 2 times x2 minus 3 times x3. Okay, can see it? Okay, and then the next bit is okay, in the exam you don't need to write. Okay, later I will tell you. Okay, just for now I need to tell you the whole process first. Okay, I tell you the whole process. Later I'll tell you what to skip. This one is to convince you that a vector equation is the equivalent to a augmented matrix. Okay, from here you get a system of linear equation. Okay, let me jot it down for you. System linear of linear equation. Okay, from here, is it obvious that you can get the augmented matrix? Is it obvious you can get augmented matrix? Okay. Okay, so you extract out the coefficient with the constant. The coefficient is minus 4, 2, 6, 3. B1, B2, and B3. Okay, so in the exam, right, you can skip this part. Okay, straight away go and get this augmented matrix. Okay, so you need to be experienced with getting this augmented matrix. Alright, this is what you need to learn. So they will have a different way of asking. So you need to know what augmented matrix you need to get. Okay. So you can see that, okay, there's a lot of things to see here. Okay, let's see what we can see. What's the time? 5:50. Okay, let's finish here and then like, not here. I mean, after I finish, then we go. So, yeah. So there's a lot of things to see here. So you can see that if you straight away go from the top to augmented matrix, actually this term here disappeared. This vector here disappeared, right? Because this vector here actually lie inside here. Remember? Okay, so this vector here disappear. Second, if you learn matrix vector multiplication before, you should learn that you take the row, multiply the column, row, multiply the column, row, multiply the column. Actually, you can straight away get this matrix by skipping the middle step, right? So why we want to introduce this trouble into it? Okay, why we define it differently? Because we use vector to define matrix multiplication. Okay, so we pretend we don't know how to multiply these two matrix and vectors together, and then we use vector multiplication. Okay, scalar multiplication and scalar addition to define matrix multiplication. Okay, this is just a formality. Okay, that's why we have this extra step here, because we go through because, okay, let me write down, because since we define matrix vector product using the using scalar multiplication and vector addition. Okay, that's why we have this extra step here. Otherwise, we can just jump from first step to the third step. Okay. What's the next? The next is row reduce this. Okay, let's skip the step. You can go and check yourself. Okay, this one leave is as a homework, and then I'll give you the end product. So the end product by the calculator is, have you guys heard a news on the chat GTP? Is it chat GTP? What do you call it? GPT, right? Okay. Have you heard the news of it? AI. So basically that AI can explain almost all the questions perfectly. Not like Google, you need to choose. He already pick the best answer for you. Yeah. So they say that maybe human will lose job to AI because AI can answer everything almost. If you give okay, yeah, I think there's a news says that they write a code. Yeah, they ask the AI to write a code, and also ask the AI to write the essay. Okay, but AI write in computer form, right? But the teacher need handwriting, right? So that guy create a 3D printer to write it. So AI write on the computer, and then the 3D printer write down the script. Yeah. So yeah, not sure what's going on. Okay, so after you row reduce this, you will get this matrix row reduced echelon form. Okay, you can see that this is this augmented. Okay, this linear system is not always consistent. Okay, why is it not always consistent? Because if you have let me set this term is b. If b is non-zero, then I will write something maybe doesn't seem make sense to you. It's false. Can you see this or not? So okay, so you can see that you can see this from this RREF. Okay, this RREF. Okay, if this term here is non-zero, okay, then you get some equation equal to non-zero, which is contradiction, impossible. So this is not consistent. So the linear system is consistent only when b equals to 0. Okay, makes sense. Okay, any question or not? There's nothing weird happening here, but you need to understand what is it going on. Okay, there's nothing weird happening here. Okay, let's just give you a flavor. Okay, I give you a flavor. So let's put 5 more minutes before I let you go. So how to say? Okay, let's put down here. Is it big enough? Okay, make it big. Okay, so let's look at this here. There's nothing special here, but you need to convince yourself. So in this case here, we will see that the linear equation is S2 equals 0, and then 0x1 plus 0x2 equals to 2. Okay, which means 0 equals to 2, which is absurd, crazy. Okay, which is a contradiction. So you need to make sure if you have a row of 0 here, the last constant term must be 0 as well. Okay, this is what I want to say just now. Okay, because 0 cannot equal to something non-zero. Okay, so this term must be 0. So which means this last term here must be 0. Okay, can I make one conclusion before we leave? Let's make one conclusion before we leave, and then the tutorial question I left you do at home. If you have any more questions, we can ask tomorrow. So the theorem is these four statements are equivalent. So first, for each vector in Rm, if the equation Ax equals to B has a solution, okay, you row reduce it and then you found the solution. That means every B is a linear combination of the column of A. Okay, so what does this mean? So so you should imagine your A, split your A into columns. Okay, split your A into columns. And then B is a linear combination. Remember what's a linear means? Vector cannot be square. And then combination is scalar multiplication and vector addition. So let's write X in a proper form first. N. And then B will be a linear combination of these two. So you got N vectors and number. How you combine them? You just mesh them one by one. Two. in. Okay, so let me move this guy down here. Okay, let's move this guy down here. Okay, and then oh, I think I missed something. So C is the column of S span RM. Okay, what span RM means? So span meaning definition. Span. The set of vector span A if every x in A is a linear combination of vectors in the set. Let me write what set is better. Omega sum. Okay, let me label this set. Okay. So these two actually, if you don't understand, these two actually is the definition of span. Okay. If still confused, tomorrow we will say again. Okay, you can raise out and then we will explain again. Maybe I will explain again spanning. And then D is A has a pivot position in every row. Okay, you can see that just now here, it is only true when B satisfies this equation here. It is not true for all B. Okay, if it is true for all B, you have to have what? Have pivot position in every row, but you don't have pivot position in the last row here. Okay. Okay, never mind. I will repeat this again next lecture for the spanning part. Okay, and then maybe we revisit a little bit again on this part here. And then try and do exercise. And then tomorrow is the 8 o'clock class. I'm not sure how many of you will show up. So let's see. See you tomorrow.
啊，哎，怎样？
我这俩 B2，
对，他俩 B2
啊？算错了？
不是，
这
这个作业呢？
这老师，你确定这是 B2加4B啊？
感觉不是。哦，B1 是 B，太小，我刚才看错了。
哎，不错了，对，
什么？
不错了。
是啊，现在也是。可以。
用了，
可以这样。
那个，
哪个？
这个东西，它不是个集合吗？它是个集合吧？
啊，它是啊。
然后它的里面的成员是这样的，
哎，这样的东西。
不是它里面成员，它之前学的时候是这样的东西。
啊，我刚才不是跟你说吗？一开始
啊，
哎，我刚才不是跟你说，哎，一样的，只是我把它写横写直吧。哎，还有不是有说过，哎，本来是这样吗？好吧，我不要写横写。说。
那用这个符号随便就可以加吗？它原本不是，它原本不是。
哦，stable。
不是，那所以它原本这个也
一样的
的时候算乘法的时候，也应该用的是矩阵乘法的。
不能啊，本来就不能乘。
为什么？
我们写 double 的时候也不能乘。
不是，那矩阵可以有乘法，那它是不是也可以有乘法？
矩阵的乘法我们是要有那个 size 要对，但是这个是 n 乘1跟 n 乘1，它不对，它不合。你一定要 m 乘。
哎，我可以乘一个1乘1的嘛？我可以乘一个1乘1的。我就乘一。
所以你现在意思是说，你把它看成一个矩阵，而不是一个向量，你明白吗？向量也是一个矩阵。
那它
刚才我故意 skip 掉。
这种括号也是一个，它是什么？它是矩阵，是向量，
两个都可以。
我好像有
好像有这个词，好像有这个词，但是通常我们写 vector 的时候会写成这样子，
对对
也
还有，
也
我想翻翻你的笔记哈。
OK，
我想，为什么没有鼠标？
你要干嘛？
我要回来。
哦，在那边啊。
来，
我想看前面那个有一个你算的那个 C1 C2那个。
啊，不在这里耶，在这里耶，哪一个？哪一个？忘记了，好像
三个，然后只有两个。
你要找答案还是什么？
不是，我想看那个，我算出来答案不太对劲的样子。
哦，那个答案会不会在这里？那个是什么？好像是一个项，但是
是说
这个是这个啊？
一个向量可以等啊？对，
我没有算过
我记得
啊，我没有算过这个，我还没有算到。
那不这个，
你直接对哦，
这个是不
你找出来直接
是有三个方程，它只有两个未知数？
对，没有错。
那如果它没有它两个，如果它就是化解完之后还是3，那就应该无解。
哦，它无解的情况是这样
啊，
它无解的情况是这样，就是我刚才给的情况，它如果无解的话，它就是对，最后一个是00，一个比较大的数字啊，这样就无解。你要问这个？
不是，我
啊
对，
但是也有点不
啊，
那这个所以有解吗？我觉得是不是也
这个我没有算过，
他为什么？
多。你有化简错啊？
我有换点，
哦，你有化简错。
可是我换点出来之后，第二个和第三个变成一样的。
对，不是那
第二个跟第三个化成一样的，
一样
这样有解啊，这样有解啊，
这样就有
有解有解
问题
有解，什么
你
问题？
你把2、3加一加，
好啊，你
然后右边是1，然后你把那个加出来的新数字乘上7，它的右边这两个相同的，它这左边两个不一样，那是不是说明两个实数它能够组合出？之前我们学过的那个叫什么式子？离散里面学的，
什么事？
那个叫什么？
我不知道你要讲。
哎呀，那先化简一下呗，要不然就是把它们两个加起来。就把它们两个加起来，然后变成-7、11，然后这边变成1，然后再乘7，就是-49、77，然后这个是7。
啥？你在干嘛？哦，你是变一条吧？
啊，
那条。
那然后这一条，那就是说-49x1加77x2等于7，然后那个x1加2x2
直接做啊。
等于7。
然后干嘛？
为什么它能够这样啊？
为什么不可以？为什么不可以？
哎，
它就2条线可以不同线啊。
那之前是不是讲过有一个什么数论？那个数论里面讲的那个什么？
呀，
那个叫什么东西啊？
什么？
不是倍组吗？是叫倍组吗？
哦，那个
不是两个数组合
没有，那个是那个GCD 哈。GCD
是 GCD 那里学的
啊 GCD， 然后你要干嘛？
那他那里不是说只会有一种情况能够组合出一个答案，一个数？
有这么说
啊？没有吗？
好像没有哎，没有吧？应该没有吧？没有吧？我可以直接给你不同的，有吗？哦，哎，等一下先，
啊？
那个是要有 GCD 等于1的时候哎。
什么呀
？GCD 不是
你看
等于啊，用的不是。
对啊，你这个2个 GCD 不等于1啊。
x1 x2不一定啊。
没。
不49和70不，它一定要 GCD 等于1的时候是吗？
好像是哎。
那如果不是的话，是它的倍数是吗？不对，是什么啊？不对，是 GCD 等于1是可以组合出所有数，GCD 不是1是可以组合出它的所有倍数。
那个mod 哈
啊，什么的呀？
，Congress 啊，没有，它有一个是等的，但是
就是那个扩展 GCD。
没有，他是说
扩展
他说是不是他是 mod，他不是等号，他的意思是说他可能是 mod，就是这个是 mod
的什么意思啊？两边同时摸7，
不知道 mod 哪一个东西哦，可能 mod 一个比较大了，你还要7的话，但是我是想说，肯定是有2个数加起来可以是一个数的。
对，我知道，但是它会有两种拼法吗？我觉得不会有吧。
对。哦，你是说如果 S1跟S2是一样的话，会不会有两种拼法？
就是两种拼法都能拼到
呃
同一个数。我不是之前听过那个，
好像有，好像我也有听过，忘记了，
我听过说
我可以
不能，
去查一下，我忘记了，
我不知道那是什么定理。
好像有，好像有，我去查一下。你是说要用那个 number theory 来看的？
什么叫 number theory？
是不是？
是不是？
几点？
是 DCD 吗？
应该要默契是不是？如果要看这个东西的话，
摸七上面是000，这下面是120，
等于系的话，那就是这两个式子都默契啊。
那下面那个式子是120，
默契
上面是000。
哦，可能他是讲默契的时候才有唯一解，因为默反正默可以隔很远嘛。但是这个准的话就没有。
但是这个准的啊，因为它这个等号啊，就不是那个默契的话可以有很多解嘛，就是因为它只要是7倍数就可以，就1倍、2倍，但这个是等号，是这个意思吗？
但是你刚才在问一个问题是什么？你讲这个 S1、S2是
不是，
有
那它也不是倍数关系啊，这
对对
两个式子
对对对
也不是倍数。
对对对 OK，可以，对，等下先搞清楚你在问什么。你是说问
啊
S1、S2只有一个答案是不是？
然后我是想问的是不是有哪个定理说过，
他只有一个答案。
两个数这么组合，
就
组合出只能组合到
对，OK，我要找一下，我忘记了，好像有一点印象。
我也记得有。
OK，我看一下。OK，我看一下。
OK，
可是如果你把这个就把这个 x1挪到这边，就把7消掉的话，让它成为一个等式的话，就可以得出 x1和x2之间的倍数关系啊。
对，
所以说 x1和x2不用是唯一的吧？因为这个题它只有x1和x2两个位置。
对，可以不用是唯一，但是问题是他想知道那个跟这个有关系吗？
肯定是唯一的呀，为什么会是不唯一的？
他的意思是说，如果你把 S1等于这个东西的话，不是？你看，
这个是，但是我这里还有3个呢。
对，
有3个，所以
就肯定不是唯一。
肯定不是唯一，因为还有一个式子，上面还有一个式子。
不一定，它可以解得出，或者它解不出。它解得出就无穷数，如果解不出就解不出。
对，
它不可能只有一个解，这个题。它有解，它不可能有一个解，它不可能只有一个。给我想想，有可能。
它有3个方程，
有可能。如果是有可能，我想的是那个比较短，但是比较长的。OK， 不用紧。OK，但是我看一下这个 GCD 这个东西跟这个东西有关系。
好，你帮我看这个。
你说可不可以直接从这边东西看出来的？
就是看出来这个东西没解，但是它又算出来了。
谁算出来的？对啊，算出来了。
它算出来了，就有答案的。所以说
有答案。
这个东西我就不知道是什么。
OK。什么？你是说这个有可能算出答案给你
不是，就是这个东西它能解出来。
对。
然后我根据这个推出来，应该是这个东西无解。就是根据这个。对吧？应该出现矛盾。
这样看一下，像这个在讲什么？我忘记了，我也是要查。你是说这个算出来是没有？
这个
猜是没有。
看出来是没有。
我看一下是不是那样子看，我忘记怎样看。
就是两个数的乘上多少，然后加一加减一减。
check一下，我也忘记了那个条件是什么。有什么 GCD 的条件应该理解。
那我明天讲。
我明天。希望我今晚来得及。
拜拜。
OK，拜。
最后这个 matrix 这个相乘，它是当时为什么是这么算的？它不是一个 vector 吗？
对。
那它为什么做这个 scalar？
对，没有错，跟这个一模一样。你看，他把 matrix 拆成 column， 然后把 vector 拆成那个 scalar， 然后他把 scalar 一个一个拉出来。
vector 做 scalar。
不是对 ，vector 里面有 n 个 scalar 嘛，对不对？
那它这个相乘的话，
对，
就是那 matrix 它后面它就是这个它的这个维度就加了一个什
么叫加？
就是在这当时后面讲哪一个
？AN 就是 AM 了，就这个头。
这个对，
好像就是这个问题。
什么问题？
我找不到了。不知道在哪里拍的。
不是你要问什么？
就是问这个乘法，它这个为什么是？
就是 definition 呢？ 对，
老师，还您这个课件它是会传到哪里？
那传到那个 Moodle 上去。
Moodle 上面
对
，Moodle
Week one
Week One 上面就会有。
对对对，
它就是那个没有修改的也会传。
会，没有修改进去。
这个consistent 是什么意思？
哦，这个要回到很，你再来看。
就最后讲这个，然后解这个 B3，然后说再算出来 B3有个式子，然后就问这个它是不是
哦，因为 consistent，因为我们不是说有三角关系吗？就是所有这种 augmented matrix 跟那个 vector equation 和那个 linear function 有关系，记得吗？记得吗？
就是说这个
嗯哼
linear
你继续说。
还有那个 matrix，还有那个还有这个 vectors，它们三个其实本质是一样的。
对，所以我在讲 consistent 的时候，你要把它想成那个 linear equation 来看。
它就是这个 linear equation 里面的这个，就是看它这个式子成不成立。
看看式子成不成立？看看式子成
就
不成立？
consistent 的这个意思到
对对
底是什么？
啊
就是说